Have you ever felt like you're battling a task, pouring all your energy into it, but progress seems to stall? When it feels like the more effort you put in, the more entangled you become. This isn't about laziness or a lack of talent. It's about something far more insidious than personal burnout. And today we're going to uncover its essence. What we're about to discuss could have changed the course of World War II, and it will transform your understanding of productivity. Because, as it turns out, sometimes the most obvious solutions lead to dead ends, and the real problem hides where no one is looking. Seems incredible, doesn't it? In January 1942, Boeing's Plant 2 in Seattle was supposed to be churning out B-17 flying fortresses in such quantities that the skies over Germany would darken with their presence. Instead, the assembly floor resembled a giant industrial traffic jam. 63 B-17 bombers stood unfinished on the line, each symbolizing a broken promise that America couldn't keep. The Army Air Forces had ordered 3,615 bombers for delivery within a year. Boeing had delivered just 9 planes. General Henry Hap Arnold, commanding general of the U.S. Army Air Forces, wasn't just disappointed. He was furious. In a tense meeting on January 15th with Boeing executives, Arnold made it crystal clear. Without bombers, there would be no strategic bombing campaign. Without a strategic bombing campaign, American soldiers would face an entrenched Nazi war machine for years to come. The calculation was simple and terrifying. Stay with us and watch until the end, because what you learn next will help you avoid similar traps in your own work. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. The problem wasn't manpower. In 6 months, Boeing had hired over 30,000 employees, many of them women who had never set foot on a factory floor before. Nor was there a shortage of materials. Aluminum flowed from Alcoa faster than it could be used. The crisis was caused by something no one had anticipated. The bombers themselves were simply too complex for rapid assembly. Each B-17G required 140,000 individual parts. The wings alone needed 12,000 rivets on each side, joining 7 overlapping layers of aluminum skin to an internal framework designed to withstand forces up to 6 Gs in combat maneuvers. Traditional assembly methods, honed on smaller aircraft, simply collapsed under the weight of this complexity. Philip Johnson, Boeing's production manager, walked the floor every morning at 5 a.m. with a clipboard in hand, witnessing the same nightmare. At Wing Assembly Station Number 4, 17 workers crowded around a single wing section. They got in each other's way. One riveter would finish a seam, step back, and another would need access to the exact spot he'd just vacated. Then a third worker needed that position for another rivet line. The choreography was maddening. Johnson timed it himself, 20 hours and 14 minutes to complete one wing assembly from bare frame to final rivet. 20 hours. The British were losing bombers over Germany faster than they were being assembled in Seattle. Every Luftwaffe fighter left unopposed due to the absence of American bombers in the sky meant more merchant ships sunk in the Atlantic, more factories running at full capacity in the Ruhr Valley, more time for Nazi Germany to solidify its grip on Europe. Boeing engineers had already tried everything imaginable. They redesigned tool access points, created specialized jigs and fixtures, even experimented with different numbers of work crews, believing that fewer people would reduce congestion. Nothing worked. The fundamental problem remained unchanged, the rivet pattern specified in the engineering blueprints. required work crews to access the same physical space in an overlapping sequence. It was impossible to parallelize the work. You couldn't add more workers to speed up the process. It was a bottleneck embedded in the aircraft's DNA. By late January, Boeing executives were having quiet conversations about the unthinkable, informing the Army that they couldn't meet production targets. Some even whispered about bringing in Douglas, or Consolidated, to take over primary production. On January 28th, a secret memo circulated among senior leadership. The subject read, "Assessment of B-17 Program Viability Crisis." No one wanted to be the person who lost the war, because they couldn't figure out how to rivet aluminum fast enough. If you had walked into Wing Assembly Station 4 on any given morning, you would have seen what looked like organized chaos, but in reality it wasn't. The wing section lay on a massive jig, a 32-foot skeleton of aluminum ribs and spars. 7 layers of aluminum sheeting, each precisely cut and drilled with thousands of holes, awaited attachment in a specific sequence. The process began at the wing root, where it would eventually attach to the fuselage and moved outward toward the wingtip. It sounds straightforward, but it wasn't. The engineering blueprint dictated that rivets be installed in rows running parallel to the wing's leading edge, the first row, then the second row, then the third, moving backward towards the trailing edge. This pattern made perfect structural sense. Each row reinforced the previous one, creating an overlapping shingle effect that distributed stress across the wing's surface. Engineers at Boeing's Seattle Development Center calculated the position of every rivet to optimize the strength-to-weight ratio. On paper, it looked beautiful. On the factory floor, it was a disaster. Here's why. To install the first row, the riveter worked from the top surface, while the bucker, the person holding the bucking bar, worked from underneath through the wing's internal structure. They had to be perfectly synchronized. The riveter's pneumatic gun drove the rivet through pre-drilled holes with 3,000 pounds of force. The bucker's bar pressed against the rivet's shank from the opposite side, forming the molten aluminum into a mushroom head that secured the sheets together. A half-second delay resulted in a weak rivet that had to be drilled out and replaced. This added 3 minutes for every error. Multiply that by 12,000 rivets, and errors became catastrophic. But the real nightmare began when the second row started. To access the second row's rivet line, workers needed to occupy the exact space where the first row crew had just been working. Except the first row wasn't finished. Not entirely. Quality inspectors needed to check every 10th rivet with a borescope, a tedious process that took 15 minutes per wing section. So the second row crew waited and waited. Meanwhile, the third row crew, already ready to work, stood idle. The production schedule called for parallel workflows, but the physical reality of the wing's geometry made it impossible. You simply couldn't fit enough workers around the structure to rivet multiple rows simultaneously. The clang of the rivet guns seemed to shake not just the metal, but time itself. These tools were not elegant instruments, but powerful pneumatic hammers that transmitted every vibration through the operator's body. Compressed air hoses snaked across the factory floor like mad pythons, constantly tangling with electrical wires for inspection lights, creating trip hazards for workers rushing from one station to another. To move from point A to point B, a riveter had to unhook their hose, coil it, navigate around 3 colleagues, find a new connection point, hook up again, and resume work. This 30-second ritual repeated 70 times for each wing section, On top of that, the shop floor suffered from an overheating problem. Even though it was Seattle in January, it was hot inside. 17 workers, concentrated around a single wing section, each generating heat, and each pneumatic gun adding its share of warmth to the confined space. The aluminum skin absorbed this heat and expanded, albeit microscopically. Just 0.003 inches for every 10 feet. But when pre-drilled holes with a 0.02-inch tolerance needed to align, that expansion meant the holes didn't match. Riveters spent 15% of their time using tapered reamers to enlarge holes that shrunk as the metal cooled. None of this was in the engineering specifications because no one had anticipated 17 people working in such close proximity for so long. Stay with us and watch until the end, because we'd be especially grateful for a like and a subscription. And of course, don't forget to tell us in the comments where you're watching this video from. Frank Szymanski didn't look like a man who could change the course of a war. 31 years old, 5 feet 7 inches tall, his hands permanently stained with aluminum dust and grease. Before the attack on Pearl Harbor, he had worked at a Chrysler plant in Detroit, installing door panels on Windsor sedans. It was repetitive, monotonous work where his hands moved ahead of his thoughts. When Boeing started hiring in late 1941, Frank moved his wife and 2 daughters to Seattle, rented a room in a boarding house near the plant, and joined the swing shift at Wing Assembly Station 4. His workday started at 4 p.m. and ended at midnight, 5 days a week, sometimes 6, when production quotas demanded it. What distinguished Frank wasn't his riveting skill. Dozens of workers could match his speed and precision. His distinction was that Frank couldn't stop observing the entire process. Most riveters focused on their immediate task: align the gun, pull the trigger, move to the next rivet, repeat 400 times a shift. Frank saw the entire ballet. He noticed that Jenkins, working on the 3rd row, always waited for Patterson to finish the 2nd row. He noticed that Patterson always waited for quality control to approve the 1st row. He noticed that this sequence created a cascade of delays that geometrically compounded as they progressed across the wing's surface. On February 4th, during his midnight break, Frank sat on an overturned parts crate, eating a salami sandwich, and staring at a finished wing section being moved to final assembly. Something about it bothered him. The rivet pattern looked perfect from a structural standpoint. Each row overlapped the previous one, creating that shingle effect the engineers loved. But Frank kept thinking about his old job at Chrysler. When they installed door panels, they didn't start at one edge and move across the entire surface. They started at the 4 corners simultaneously and moved towards the center. Why? Because it allowed 4 workers to work in parallel without getting in each other's way. The geometry of the door panel made parallel work possible. He looked again at the wing diagram posted on the station's bulletin board. The rivet pattern ran in straight lines from the leading edge to the trailing edge, parallel rows marching across the wing's surface. But the wing itself wasn't a flat rectangle. It was a complex 3-dimensional structure with depth, with internal ribs creating separate compartments, with access points at specific locations. What if the riveting sequence followed the actual geometry of the wing, rather than treating it as a flat sheet? What if you started at multiple points simultaneously? Points chosen because they gave workers maximum physical access without overlap. Frank grabbed a pencil and began sketching on the back of his time card. Instead of straight rows, he drew a pattern that looked almost random. Rivets clustered around structural ribs where access was easiest. Then diverging lines connected these clusters, following the natural contours of the wing's internal structure. It looked wrong. It looked like someone had spilled rivets on the blueprint and decided to leave them where they fell. But as Frank traced the pattern with his finger, he realized something critically important. 5 workers could rivet simultaneously, with none of them requiring the same physical space. Worker number 1 could be at the wing root inside the main spar. Worker number 2 could be in the middle of the wing, accessing through an inspection panel. Worker number 3 could be working on the trailing edge, which was shallow enough to rivet top-down without bucking. They would never intersect. His concern was the structural implications. The engineering blueprint specified that parallel row for a reason. Load distribution, stress concentration, terms Frank only half understood. But he kept thinking about something else he'd noticed. Rivet failures almost never happened where 2 rows met. They happened at transition points, where the wing skin changed thickness, or where cutouts for fuel tanks interrupted the pattern. The rows themselves weren't magical. They were just one way to distribute fasteners across the surface, perhaps not the only way. Frank knew what would happen if he approached a production supervisor with his sketch. They would politely smile, tell him the engineers had spent months calculating those rivet positions, and send him back to his station. The hierarchy at Boeing Plant 2 was rigid. Engineers designed, managers managed, workers assembled. No one expected innovation from a guy whose job title was Riveter Second Class. Have you ever thought that such a seemingly simple action as riveting could become a stumbling block for an entire aviation giant? That an ordinary worker could challenge established engineering principles, risking not only his career, but also the fate of an entire company? Prepare to hear a story that will overturn your understanding of manufacturing and innovation. This is the story of how one man's courage and another's unconventional thinking changed the course of aviation history when it seemed all was lost. While many workers at the Boeing plant, like cogs in a vast machine, dutifully followed instructions, Frank, a mere riveter second class, possessed a unique advantage. His shift, the so-called swing shift, was led by Bill Hendricks, an extraordinary man. Hendricks, who started as a simple sheet metal worker, had risen to a supervisory position by 1940 but hadn't lost touch with the everyday workers. He genuinely listened to those on the shop floor, which, depending on one's perspective, made him either remarkably progressive or dangerously naive. It was to him, during the shift on February 11th at 8 p.m., that Frank approached with his sketch. Hendricks studied the drawing long and thoughtfully. Then he uttered words Frank had not expected. This contradicts every principle of structural loading Boeing uses. You know that, right? Frank nodded. He knew, or at least he suspected. Hendricks continued, delving into technical details. The parallel rivet pattern isn't accidental. When a wing flexes under load, stress concentrates along predictable lines. The rivet rows are placed perpendicular to these stress lines. These are fundamentals, the basics. It's written in every aerospace engineering textbook published since 1927. The principle Hendricks described was the result of work by Theodore von Karman and his team at Caltech in the late 1920s. They mathematically proved that fastener patterns in load-bearing structures must align with stress trajectories, the invisible lines of force that pass through metal under pressure. The B-17 bomber wing, carrying 6,500 pounds of fuel plus the structural weight of 4 engines, experienced colossal bending stresses during flight. The bottom surface was under tension, trying to stretch. The top surface was under compression, trying to contract. Directly in the middle, along the neutral axis, the stress approached zero. Von Karman's equations showed that fasteners should be densest, where stress was highest, and could be sparser, where stress was minimal. The parallel row pattern perfectly achieved this. Each row corresponded to a specific magnitude of stress, and the spacing between rivets was calculated according to load requirements. Stay with us and watch until the end, for which we'd be especially grateful for a like and a subscription. And, of course, tell us in the comments where you're from so we know the geography of our viewers. Frank's proposed scheme completely disregarded all these principles. His clusters placed dense groupings of rivets around structural ribs, not along stress lines. His radial connections followed convenience of access, not load paths. From a classical engineering perspective, it was complete absurdity. The wing might have survived taxi tests, perhaps even the first few flights. But under sustained combat loads, micro cracks would inevitably develop where the rivet pattern didn't match the stress pattern. These cracks would propagate, the wing would fail, and people would die. Hendricks explained all this to Frank on the noisy factory floor, shouting over the pneumatic rivet guns. Then he asked the question that changed everything. But did von Karman ever consider assembly efficiency as a structural factor? Frank looked confused. Hendricks continued, "If it takes us 20 hours to rivet a wing, and we're making mistakes because workers are exhausted, cramped, and tripping over each other, how many of those 12,000 rivets are actually installed to spec? How many are slightly loose because the riveter missed the buck? How many holes are slightly reamed out because they didn't align perfectly? Your scheme might be theoretically weaker, but what if it produces practically stronger wings because the quality of installation is perfect?" This was tantamount to heresy. Boeing's quality control processes assumed that workers followed procedures correctly. Procedures were designed based on engineering specifications. If wings failed quality inspection, workers were retrained or fired, and better ones were hired. The airplane was not redesigned to accommodate worker limitations. This was backward thinking. It was like the tail wagging the dog. However, Hendricks, in his 3 years as a supervisor, had seen something different. He had noticed that theoretical perfection and practical reality diverged far more than engineers wanted to admit. He had seen riveters, exhausted by the 18th hour of wing assembly, trembling with fatigue. He had seen buckers miss their mark because they had been in the same position for 40 minutes, and their legs cramped. He had seen quality inspectors approve slightly loose rivets because rejecting them would mean another 2-hour delay, and production quotas were already impossible. What if Frank's incredible scheme, by reducing assembly time and worker fatigue, actually ensured more reliable and perfect installations? Stay with us and watch until the end. We would be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching from, so we know the geography of our viewers. Hendricks folded Frank's sketch and put it in his pocket. "I'll talk to someone," he said. Frank returned to his rivet gun, expecting nothing. Hendricks didn't go to the chief engineer. That would have been suicide. Oliver Eccles, Boeing's head of engineering for the B-17 program, had a reputation for eating alive shop supervisors who dared to challenge his designs. Instead, Hendricks went to Donald Douglas, no relation to the aircraft company, who was an assistant production manager and had 3 weeks until he was fired if production numbers didn't improve. Douglas was desperate enough to listen to even the craziest ideas. On February 18th, Douglas glanced at Frank's sketch for about 30 seconds before saying, "This is trash. Get it out of my office." Hendricks didn't move. He pulled out his notepad and showed Douglas something else. Assembly time logs from Wing Station 4 for the past 6 weeks. Each wing took between 19 and 22 hours to assemble. Not a single deviation. Not a single crew found a way to work faster. The bottleneck was structural, built into the process itself. Douglas looked at the numbers, then back at the sketch. Even if this works efficiently, Eccles will never approve it. Never. He'd sooner shut down the plant than rivet a wing using a non-standard pattern. Here's what Douglas understood, and Hendricks didn't. Boeing was weeks away from completely losing the B-17 contract. Consolidated Aircraft was actively lobbying the U.S. Army Air Forces, arguing that their B-24 Liberator was easier to manufacture and could be produced in greater numbers. General Arnold was listening. If Boeing couldn't demonstrate a dramatic improvement in production by March 15th, the Army would redirect orders to Consolidated and other manufacturers. Boeing would retain some production, but lose its position as America's primary heavy bomber supplier. That meant layoffs. That meant the collapse of Seattle's economy. That meant Douglas would lose his job anyway. Have you ever felt that a system designed to help actually binds your hands and feet? Have you felt bureaucracy stifle every initiative and every attempt to improve something hit a wall of rules and protocols? Perhaps you even thought the only path to success was through strict adherence to norms. Well, get ready for us to shatter that belief today, because sometimes, to achieve a breakthrough, you don't just need to bend the rules, but to completely rewrite them. We know that feeling perfectly. When it seems like the world is against you, and every attempt to change something for the better only leads to a headache. We've been through it ourselves. But what you'll see next will change your perspective on possibilities. In this video, we will delve into an incredible story where one person, against all odds, did the unthinkable, and his audacious move not only saved thousands of lives, but also forever changed the course of manufacturing history. We will show how, by breaking dozens of protocols, one can achieve perfection that seemed unattainable. Stay with us and watch until the end, because this story is full of unexpected twists, and its lessons are relevant even today. We would be especially grateful for your like and subscription, as this helps us create more content like this. And of course, we would be very interested to know. Please write in the comments where you are watching this video from. The story is about Douglas, an engineer who found himself at the center of this whirlwind of change. His decision, made in an atmosphere of strict secrecy, violated about 17 different Boeing company protocols. He authorized testing without the approval of the engineering department, but doing so during the day shift, with senior management walking the floors, was simply impossible. The evening shift wasn't suitable either. Too many eyes. So Douglas scheduled the test for the night shift on the night of February 21st, starting precisely at midnight. He chose a wing section that had already been rejected by quality control for entirely different reasons, a damaged spar that rendered it unfit for flight. This was a calculation. If the test went catastrophically wrong, they wouldn't lose a valuable, usable wing. He gathered Frank and 4 other riveters, all veteran night shift workers, who voluntarily agreed to this risk. And he told absolutely no one else. These men were preparing to do something that could cost them all their jobs, but their faith in Douglas and his idea was unwavering. The test began at 0014. Frank had spent 3 days refining his pattern, meticulously planning exactly which groups of rivets would go where, and calculating sequences that would allow all 5 workers to operate simultaneously. He even color-coded the drawing. Red for the first worker, blue for the second, green for the third, yellow for the fourth, and purple for the 5th. Each color denoted a physical zone that did not overlap with zones of other colors. The workers could literally rivet simultaneously, without coordinating their actions, without waiting for each other, without getting in each other's way. From the outside, it looked like complete madness. Traditional riveting had its own rhythm, a logically structured sequence. Here there was a frantic but controlled chaos. One worker was inside the main spar cavity, another beneath the trailing edge, a third worked from above, near the leading edge. They weren't following rows. They were working with groups of rivets, and these groups seemed scattered entirely at random. Douglas stood 10 meters away, stopwatch in hand, nervously smoking Lucky Strikes. Hendricks stood silently beside him. Every 15 minutes, Douglas checked his watch and recorded the time. No one could have predicted that this chaos would lead to incredible efficiency. By the way, friends, if you're still with us, that's a great sign. Stay until the end, because the climax of this story is yet to come. Please like this video, subscribe to the channel if you haven't already, and of course let us know in the comments which city or country you're watching from. Your support is very important to us. At the 2-hour mark, the wing should have been about 20% complete, but it was already 45% done. The workers began to realize that something unusual was happening. They weren't waiting for anyone, not each other, not inspectors, not access to work areas. Every rivet position marked by Frank was indeed accessible without obstruction. Pneumatic hoses didn't get tangled because the workers didn't cross paths. Heat was lower because they weren't clustered in one area. The aluminum didn't expand as much because 5 heat sources distributed across the wing surface created less concentrated thermal load than 17 sources in one spot. Now the remaining question was whether this rapid production was of the same quality. At 02:21, 127 minutes after starting, the last rivet was set. Douglas clicked his stopwatch. He said nothing. He walked over to the wing and began randomly inspecting rivets, pulling out a bore scope to check for proper bucktail formation. Chris held his breath. Frank stood, covered in aluminum dust, trying to read Douglas's expression. Douglas inspected 30 rivets before he believed his own eyes. Every single one was perfect. The bucktail heads were uniform, properly seated, with no gaps between the aluminum sheets. He called Jimmy Chen, the night shift quality inspector, without explaining what he was inspecting. Chen took his toolkit and began a full inspection protocol, the same one he had performed on the 200 previous wings. He checked rivet spacing with calipers. He used a thickness gauge to check sheet metal compression. He tapped each rivet head with a small hammer, listening for the dull thud indicating proper seating, as opposed to the hollow ring of a loose rivet. What he discovered made him question the reality of what was happening. 40 minutes later, Chen looked up and said, "It passes. I don't know what crew did this, but it's clean work." Douglas told him how long it had taken. Chen thought he was joking. Then he decided the stopwatch must be broken. After that, he rechecked his inspection because wings riveted that quickly couldn't be that clean. There had to be errors, rushed work, something wrong. He found nothing. The wing was perfect. More than that, it was better than perfect. Chen had been inspecting B-17 wings since July 1941 and kept a personal defect log he never showed management. On average, a wing would have 140 rivets requiring attention during quality control. Loose rivets, misaligned holes, installation errors. This wing had only 11, less than 1/10 of the usual defect rate. But passing a visual inspection didn't guarantee the wing would withstand flight loads. The rivet pattern was still completely wrong from a structural engineering perspective. Douglas knew they needed real tests, the kind that required equipment and authorization he didn't have. At 0330, he made another unauthorized decision. He called the Boeing test stand night shift in Building 7 and ordered them to prepare for an emergency stress test. He didn't mention that the wing used an unapproved rivet pattern. He simply said they urgently needed to test a wing section for production verification purposes. He was sending something to be tested that could collapse at any moment, violating every imaginable safety standard. The test stand was equipped to simulate flight loads. A massive hydraulic press could apply up to 68 tons of force to a wing section, bending it up and down to replicate the stresses of flight maneuvers. Standard B-17 qualification required wings to withstand loads equivalent to 2 times the aircraft's maximum weight without permanent deformation. This was the safety margin. Army Air Force's specification R8116B, established in March 1941, mandated these tests for any structural modification to production aircraft. Douglas was about to test a wing that violated R1816B in every possible way, using a facility not authorized for non-standard tests, at 4:08 a.m. when no one was watching. They mounted the wing section into the test frame at 04:15. The hydraulic press engaged, applying upward pressure that bent the wing tip upward. Douglas watched the strain gauges. At a load equivalent to 1G, the wing flexed normally. At 3G, still normal. At 6G, the deflection precisely matched specification. At 2G, the qualification threshold, the wing held. No creaking, no popping rivets, no crack formation in the aluminum skin. Douglas told the operator to continue. At 7G, the wing was still structurally sound. At 8G, individual rivets in the wing root began to show stress. But this was expected. The wing root bore the highest loads and should have been the first point of failure. At 4G, the test was stopped, not because the wing failed, but because Douglas was scared to death of breaking the test equipment. Have you ever wondered if the strongest structures in the world might not be the result of precise calculations, but a stroke of genius accident? What if I told you that once, at the dawn of the greatest war, an aircraft wing, designed by a man with no engineering degree, refused to break when it should have? It defied all laws of physics and conventional wisdom. You're used to believing in immutable rules, but this story will show how one seemingly insignificant deviation from the norm can lead to absolutely incredible results that will revolutionize an entire industry. Imagine, engineers had spent decades learning to build aircraft one way, trusting every bolt and rivet. But what if that path was a dead end, and only one bold experiment, essentially an error, could lead them out of it? Today, we will tell the story of a breakthrough that revolutionized aircraft manufacturing and changed the course of World War II. You'll learn how an ordinary worker, against all odds, created something that exceeded all expectations, and why his name remained unknown. This isn't just a story about airplanes. It's a story about how one small detail can change the world. And to not miss a single detail of this amazing saga, stay with us and watch until the end. We would be especially grateful for your like and subscription, and of course, don't forget to write in the comments where you are watching this video from. Let's return to the tests. When the hydraulic pressure was released, the wing returned to its original neutral position, showing absolutely no residual deformation. Not the slightest. This was unheard of. By all engineering standards, a properly designed wing, after a load of 8. 4G should have shown at least microscopic residual deflection. However, this wing remained flawless, as if it had only been subjected to 5G. Chen again ran his inspection protocol, carefully examining every rivet that had been subjected to maximum load. Not one had loosened. Not one showed signs of microscopic slippage. The wing somehow proved stronger than all its counterparts built to standard blueprints. At dawn, at 5:47 a.m., Douglas stood, stunned by what he had seen, trying to comprehend the incredible reality. He realized that Frank's pattern, which placed clusters of rivets around the main spars, the primary load-bearing elements of the wing, accidentally created a scheme that did not fight against the natural load distribution paths, but rather amplified them. The radial connections between the rivet groups acted as secondary stress distributors, diverting load away from weak points. This was not a random arrangement. It was organic. It perfectly matched the actual flow of forces through the structure, not how engineers thought they should flow. By 6 a.m. on February 21st, Douglas understood clearly. This information needed to be immediately brought to someone with the authority to sanction full-scale implementation, and certainly not to Eccles, who would kill the idea in its infancy on principle. He headed straight for James Murray, Boeing's Vice President of Manufacturing Operations, waking him at his Laurelhurst home. Murray arrived at the plant at 7:15 a.m., still in his dressing gown, and demanded all the data, test results, inspection reports, timing. He watched intently as Douglas's trembling hands explained what they had done without authorization. Murray's face remained impassive. Then Murray asked the only truly important question. Can we train 200 riveters to use this pattern by Monday? Douglas hadn't looked that far ahead. He had been so focused on proving the concept worked that he hadn't thought about scaling it. Murray, however, was already doing the math. If one wing took 2 hours instead of 20, and Boeing had 42 wing assembly stations, that meant a 10-fold increase in wing production, without hiring a single additional worker. Wings were the bottleneck. Fuselages were being assembled faster than they could be joined to wings. Tail sections piled up, waiting for completed aircraft. The entire production line was limited by the speed of wing assembly. Solve that problem, and everything else would flow. That morning, Murray made a decision, overriding Eccles's vociferous objections, the engineering department's protests, and the Boeing legal team's grim warnings about potential liability if wings failed in combat. Murray ordered the new rivet pattern implemented across all production lines starting February 25, 1942. He raised Frank Szymanski's pay by $40 a week and gave him the title Production Methods Specialist. He promoted Chris to senior supervisor. He assured Douglas his job was safe, and he told Eccles that if he didn't like it, he could explain to General Arnold himself why Boeing was still only building 14 bombers a month. The results were staggering. In March 1942, Boeing Seattle delivered 47 B-17s. In April, 91. By June, they hit 186 aircraft. But the real explosion came in July, when all 42 wing assembly stations were fully converted to Frank's pattern, and workers had mastered the new sequence. July production, 2 A-84 B-17s, August 319. September, 362 bombers rolled off the line in a single month. This exceeded the entire annual output of 1941. The impact on the air war was immediate and devastating for the Luftwaffe. In October 1942, the 8th Air Force conducted its first raid with over 100 bombers attacking industrial targets in Lille, France. The Luftwaffe was designed to fight defensive battles against raids of 20 or 30 bombers. They could swarm such formations, pick off stragglers, making each mission costly enough to be unsustainable. But 100 bombers, the defensive fire from that many B-17s created overlapping fields of fire that made fighter attacks suicidal. German pilots called it the wall of lead. They were losing 3 fighters to shoot down 1 bomber, and the Americans kept coming. By January 1943, the 8th Air Force was flying 300 bomber missions. By summer, 500. Each of these aircraft represented 2 hours of riveting instead of 20. Each carried 4,000 pounds of bombs deeper into Germany than Hitler thought possible. The Schweinfurt-Regensburg missions in August 1943, the raids that crippled German ball-bearing production, required 376 B-17s. Without Frank's pattern, Boeing would not have built that many bombers by August 1943. The entire strategic bombing campaign, the effort that diverted German fighters from the Eastern Front and forced the Luftwaffe into an unsustainable war of attrition, depended on Boeing's ability to flood the skies with flying fortresses. Boeing Seattle was not the only plant using Frank's pattern. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had all adopted variations of the method. Combined production across all facilities reached 512 heavy bombers in a single month. The Germans were producing 1,000 fighters monthly to counter them. But it didn't matter. You cannot win an air war when the enemy builds bombers faster than you shoot them down. Frank Szymanski never became famous. In July 1943, he received a commendation from the War Production Board, a certificate signed by someone he'd never met, and it hung in his daughter's bedroom until she moved out in 1959. Boeing gave him that raise and impressive title. But after the war ended, during the 1946 downsizing, the positions of production methods specialist were quietly eliminated. Frank returned to Detroit, worked for Ford for 23 years, and died in 1971, never knowing that his rivet pattern had fundamentally changed the way aircraft were made. He truly changed everything. Not immediately or obviously, perhaps, but the principle Frank stumbled upon became doctrine. In 1947, when Boeing began designing the B-47 Stratojet, its first swept-wing jet bomber, engineers didn't start with theoretical rivet patterns. They began by consulting assembly line workers about access points and workflow. The B-47 wing used a pattern that looked chaotic on paper but could be riveted by 6 workers simultaneously in 3 hours. No one called it the Szymanski method. No one knew there was a Szymanski. They simply knew that aligning rivet patterns with the reality of assembly rather than pure structural theory resulted in better airplanes faster. Imagine a situation where for years you perform the same job day after day and see how it could be done better, faster, more efficiently. But your ideas go unheard because you're just a rank-and-file worker, not a degreed engineer. Sounds painfully familiar, doesn't it? Perhaps you too have encountered situations where the most brilliant theories, developed in comfortable offices, shatter against the harsh reality of the factory floor. How is it possible that someone unburdened by academic degrees can see an obvious solution that eludes entire teams of highly educated specialists? Today, we'll tell you an incredible story that not only radically changed approaches to aircraft manufacturing, but also taught an invaluable lesson about the importance of every link in the product creation chain. You'll learn how one person, armed only with observation and practical experience, made a breakthrough that still shapes the principles of global mechanical engineering today. And the most surprising thing, his name is undeservedly forgotten, even though his secret became the basis for teaching in leading technical universities worldwide. Prepare for your perception of true experts to change forever. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching from. Precisely such a story unfolded in 1942, when Boeing factories were buzzing with work on the legendary B-17 bomber. Production demanded colossal effort, and every hour of downtime was precious. At this critical juncture, Frank Szymanski, an ordinary worker riveting wings, suggested changing the customary order of rivet installation. His idea seemed paradoxical. The theoretically optimal pattern developed by engineers was slow and inefficient in practice. Frank, however, proposed a pattern that might not have looked ideal on blueprints, but significantly sped up the process without compromising strength. His intuitive solution reduced the riveting time for B-17 wings from 20 hours to 8, demonstrating that practical knowledge sometimes surpasses pure theory. This principle, born on the factory floor, quickly found broader application. Douglas Aircraft implemented similar approaches when building its DC-8 airliner in the late 1950s. Lockheed followed suit with the C-130 Hercules military transport aircraft. And when Boeing began developing its first commercial jet airliner, the 707, their engineering team took an unprecedented step. They invited assembly line supervisors to participate in initial design reviews. This was a truly revolutionary concept, asking those who would actually build the aircraft how well its design lent itself to assembly. The 707's fuselage panels used what Boeing internally called cluster riveting. It was Frank's pattern, but under a corporate name. It reduced the 707's fuselage assembly time by 60% compared to its predecessor, the Stratocruiser. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching from. However, the true legacy of this story manifested in the modern philosophy of aerospace manufacturing. There's a principle known as design for manufacturability, DFM, that every aerospace engineer studies in university. Today it states that design elegance is measured not only by its performance, but also by the efficiency with which it can be built. The classic example taught at MIT, Caltech, and every aerospace engineering program worldwide is the riveting of B-17 wings. How a theoretically optimal pattern proved inferior to a practically optimal one. How reducing assembly time improved quality rather than degrading it. Most students will never learn about Frank. They study Boeing's innovative manufacturing methodology development program as if it were a committee decision. Modern aircraft, such as the Boeing 787, take this idea even further. The 787's fuselage sections are joined using computer-generated fastening patterns that appear random but are actually optimized for robotic installation. Each pattern is generated by algorithms that simultaneously consider structural loads, assembly access, thermal expansion, and about 20 other variables. Frank did the same thing in 1942, using a pencil and a timesheet. He simply didn't have the mathematics to prove why it worked. He had something better. He had advanced pattern recognition, gained from observing thousands of rivets being installed and noticing what slowed everyone down. This is the inconvenient truth this story reveals. Frank wasn't smarter than Boeing's engineers. He wasn't better educated. He didn't understand von Karman's stress equations or load path analysis. He had a different kind of knowledge. He knew how tiring it was to crouch in one position for 40 minutes. He knew how pneumatic hoses got tangled when workers crossed paths. He knew that theoretical perfection, executed poorly, yielded worse results than theoretical imperfection, executed flawlessly. Boeing's engineers knew how to calculate stresses. Frank knew how to actually build things. Both types of knowledge were necessary. Only one type was valued. The aerospace industry eventually realized this, but it took decades. Modern aircraft development uses integrated product teams, where machinists and assemblers work side by side with engineers from day one. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers had veto power over design decisions that could make manufacturing impossible. This is Frank's true legacy. Not a specific riveting pattern, which is now obsolete in the age of automated fastening systems. The legacy is the idea that the person doing the work might understand it better than the person who designed it. Revolutionary in 1942. Common sense now. Except we keep forgetting and having to learn it again. Every innovation cycle generates its own Frank Szymanski, someone who sees an obvious solution that experts are too educated to notice. Smart organizations listen. The others keep riveting wings for 20 hours and wonder why they're losing.